How you doing? My name is Andrew Phillips. I'm an electrical engineer. I'm here with my teammates Andrew Vos, electrical engineering, Andrew Ramirez, computer, and Jane Trapala, computer. So we work under the Capstone design project of FM approvals to create an automated response time measurement for gas detection equipment. For a little bit of background on FM approvals, they provide third-party testing and certification services for loss prevention equipment for commercial and industrial purposes. So one of the things that FM certifies is their gas detectors. As you can see here, on the upper right, you have where the gas detector shall go in their apparatus, and you have the lower chamber and upper chamber, which will hold water, and two manual valves here and here to control the flow of test gas. For a little animation on how this works, is you have the test gas tank here, and you have the valve. You will open the valve, allowing the test gas to go into the lower chamber. When the gas goes in the lower chamber, the water level goes down from the lower and up to the upper chamber. Once you reach a certain level, you want to close that manual valve. Then, when you're ready to start the testing process and allow the test to go to the gas detector, you want to open the large valve, allowing the water to go down and the gas to go up to the gas detector. While this current apparatus works fine and everything goes great, they really want to refine this by automating the testing process. But how will this be done? Firstly, we want to remove the manual valves and automate them. That means taking away the large valve and the gas inlet valve and replacing them with two automated valves. Secondly, we like to automatically and reliably allocate the data. That means using a computer interface connected to the gas detector to directly get the values that we want to take.
FM approvals would like to automate their current test apparatus for two main reasons. The first reason being to reduce the cost. This is done by reducing the need of 2 employees conducting the test down to 1. The second is to produce reliable and accurate results. Automating the test apparatus will take the factor of human error out of the equation. The first step in automating the apparatus was to replace the manual valves with automated valves. As you can see here, we've replaced the large ball valve with a knife gate valve and the smaller ball valve with solenoid valves. These were chosen because they open up very quickly in under a second. It will not interrupt the flow of test gas up to the gas detector. Here's a picture of the current fully automated test apparatus. The knife gate valve is mounted on top of the lower chamber with 2 solenoid valves on either side of it. These solenoid valves supply compressed air to the pneumatic valve and allow it to open or close. Below this are another 2 solenoid valves, one to allow test gas to enter the lower chamber and another to allow compressed air into the lower chamber to purge the stagnant test gas up out of it after the test has been conducted. To power and control these components, we're using a power supply, power bus, Arduino, and relay module. Together, the Arduino and relay module will send signals to the solenoid valves to allow them to open or close as needed.
Besides controlling the test apparatus, the Arduino also reads and allocates the lower explosive limit percentages every half second and sends that to our GUI. We created our GUI so that the person conducting this test can start it and also view data throughout the test. We designed this GUI to control the entire test process and display data and the status of it. Before starting, you may be wondering, how exactly does our GUI work with the test apparatus? Well, before we begin the test, the user would want to input certain information such as the customer name, the ID, test location, and test equipment number. Once that information has been inputted, the user will then go ahead and press the connect button, which would open a serial communication between the Arduino and the GUI, allowing them to communicate with each other. To show that it has been opened, we also create a small text box right here that will display the serial port has now been opened. When the user is now ready to begin the test, they'll go ahead and press the start button here, which would make the GUI write to the Arduino to go to the next state of the test. Any status updates that happen with the Arduino would also be shown in this large text box shown here that will display any state that we're in during the test. Once we get to the portion of reading the lower explosive limit percentages, we implemented a feature that will graph each percentage every half second in real time until the 90 seconds is up. To eliminate the need of a physical stopwatch, we also implemented a stopwatch shown here in our GUI that currently adheres to the timing standards of 90 seconds for the LEL percentage readings. As for our data acquisition, we are currently generating a CSV file at the end of the test that contains all the data points of the lower expected limit percentages that we allocate every half second, as shown here. Once we generate that CSV file, we'll load that data into our SQLite database, but we didn't want to stop there. We came up with the idea that we could possibly auto-generate the test report itself. So to begin with this, we created a Word template that is a replica of a report used by FM approvals that indicates whether the test has passed or failed. What we intend on doing is using the backend to fill out the details, such as the information we entered in the beginning of the test and the information we gathered with the LEL percentages shown here. If we are successful in doing this, we will surpass the data acquisition mentioned in our current anticipated best outcome. We will now talk about our future.
So with a good amount of progress done, we have a clear view of what's to come next. So one of our focuses is data. This includes any GUI refinements. Any single details that we would like to add on there is part of that. The next thing is creating an efficient test report package. Currently, our implementation is to open up an instance of Word in the backend, but we would like to change this to a plain XML template. The next thing is working with our SQLite database. We currently have a test database up and running, but we would like to make sure that this is as solid as possible. So this means just adding all our data from the test runs and analyzing that data so we can have a pass-fail baseline and we can send error messages whenever something looks wrong. The next thing and finally, we would like to wrap everything up in an installer package. So this makes it easier for the technician to install it into any laptop that they work on. And for our hardware, we will be focusing on documentation. We'd like to make this as easily repairable as possible. Since we are setting new global standards, we want to make sure that everything is ruggedized. So this includes creating Arduino housing, and for the smaller components as well, and recreating the mountain bracket. Currently it's plastic, and we would like to change over to something that is metal so it can withstand heat. The next thing, we would be including some of the edits from our GUI and just having those sync with the hardware. So this means changing some of the valve settings and modifying sampling rates as a technician would like. And lastly, instead of manually inputting the measurements for the ambient temperature, humidity, and pressure, we'd like to add sensors so it's auto-generated in there as well. Our goal is to just have the technician sign off on the report at the end. And with that, we would like to thank the following people for their support.